Now we are looking at graphs of functions. And looking at the graphs of functions, you should be able to give information about the graph. So after today's video, I'm hoping that you'll be able to identify the graph of a function. So looking at a graph, you should be able to tell, is this a function or not? You should be able to obtain information from or about the graph of a function. For instance, you might want to know, where is the graph increasing, decreasing, or constant? You should be able to look at the graph and locate your x and your y intercepts. You should be able to evaluate a function of f of x when x equals a and find out what f of a is by looking at the graph. And then looking at the graph, you should be able to find your f of x value such that f of x is equal to some number. In this case, let's call it just b. Okay, so recall what it meant to be a function. So for a relation to be a function, each number of x in the domain, recall, has just exactly one output y in our range. So for every x in our domain, it spits out only one y value in our range. So another way to state this, this means that the graph of a function cannot contain 2 points with the same x coordinate and different y coordinates. So there is what is called the vertical line test, and the vertical line test we can use to see if a graph is a function. So the graph of a function must satisfy the following vertical line test. Okay, well, the vertical line test, what is the vertical line test? So there's a theorem, the vertical line test, and it states that a set of points in the xy plane is a graph of a function if and only if, so this has to hold true, if every vertical line that you can draw on the graph intersects the graph and at most 1 point. So if we can draw a vertical line anywhere on that graph and it intersects at most 1 time, then it would be a graph of a function. So let's look at the following examples. We're given the graphs, and with these graphs, let's determine if it's a function or not. And then looking at the graph, let's determine what the domain of the function is, what the intercepts are, and if this has any symmetry respect to the x-axis, y-axis, and or origin. So to determine if these are a function, we want to see, do they pass the vertical line test? Well, here's a case scenario where I draw one vertical line and it's intersecting the graph more than 1 time. And so since this is intersecting the graph more than 1 time, this is not a function. So there's multiple places in this graph where one x value corresponds to 2 y values, different y values. Okay, so this is not a function. But it still has a domain and range, and it still has intercepts. And so looking at this, let's look at what is the domain. So we're called domain are all the x values that you're using. And if we look at this, looking at the graph, notice that all the x values that we're using are coming in from -infinity and stopping when we hit x equals 0. So one way to write this, which we normally don't do in inequality notation, is that x has to be less than or equal to 0. Another way that we stated this in interval notation was -infinity to 0, it includes the value of x equals 0, so we put the bracket. So we're hitting all of those x values. Range, though, range is the only time that we look on the interval notation, we use our y values that the graph is hitting. So in this graph, we are actually going to hit all of the y values. This function right in here, this is continue, because those arrows are going to continue to go down as we go off to negative infinity. And they're also going to continue to go up. So we're going to hit all of our y values. So the range, we're hitting all the y values from negative infinity all the way up to positive infinity. So symmetry, looking at the graph, can we fold our paper along the y-axis and get a mirror image of each other? So if I folded my paper along this y-axis, I don't have a mirror image across there. So this is not symmetrical with the y-axis. If I folded my paper along the x-axis, notice that the piece above the x-axis would be lying on the piece below the x-axis. So this is symmetrical. To the x-axis. So the graph is symmetrical with the x-axis. So looking at the next graph, notice that you have a circle. You guys should be able to give me that equation of the circle. You guys have been looking at circles and graphing circles and finding equations of circles. Before we get into that, I noticed I forgot one thing on the last problem, which was finding the intercepts. So where is it crossing or touching the x and the y axis? Well, there's only one point where it crosses or it touches, actually touches the x and the y axis. So our intercept is at 0, 0, the point 0, 0. Okay, so going down to the next problem, we want to know, is this a function? Can we draw a vertical line anywhere on this graph and have it intersect more than one time? And so there's multiple places where we can draw a vertical line and it's going to intersect more than one time. So this one is not a function. Looking at intercepts, so where is this crossing the x and the y axis? Well, we have two spots where it's crossing the x-axis and two spots where it's crossing the y-axis. So our intercepts are the following points. So when x is -2, y is 0. When x is +2, y is 0. Those are x-intercepts. And our y-intercepts are 0, 2, and 0, -2. If I look at my domain, all the x values I'm hitting are between and including -2 and 2. These are always mapping to these y values. So our domain x we can write is between -2 and including 2. Or interval notation, we would write it with a bracket because we're including -2, comma 2 bracket. The range are all the y values you're hitting. Well, the smallest y value that we hit on this graph is -2, and the largest y value that we hit on this graph is +2. So our range is the same as our domain, except it's y values. So we have -2 is less than or equal to y is less than or equal to 2. Or if I wanted to write that in interval notation, it's bracket -2, comma 2, bracket. And then the last question it asks is about symmetry. So I noticed that if I folded my paper along the x-axis, I would have a mirror image. This piece above the x-axis would lie on the piece below. If I folded it along the y-axis, I have a mirror image. And then for the origin, if you can fold your paper in force, so across the x-axis, across the y-axis, and then they would be some lying on top of each other, a mirror image, and then it's symmetrical with the origin. And so this is symmetrical with all of them. So we're symmetrical across the x-axis and y-axis and the origin. So next week we'll learn about symmetry and how to test for symmetry given an equation. Is it symmetrical across the x-axis, y-axis, or origin? And if it's symmetrical across the y-axis, it's a special function. It's a even function. And if it's symmetrical across the origin, it's an odd function. Okay, but we'll talk about that next week. You don't need to know it quite yet. So the last equation or graph that's given to us wants to know, is the following a function or not? Well, this is a case where I can draw a vertical line anywhere, and it's only going to intersect at most one time. And so in this case, this is a function. Looking at our domain and range, we actually have what is called a vertical asymptote on our y-axis. So it looks like this graph, because of the arrow, it's continuing on, going down to -infinity. It's never going to touch or cross this x-axis. And so for my domain, I'm hitting all the x values, starting at, but not actually hitting it, from 0 to this x value here. It's not including it because it's an open circle of 3. So that's the domain. And if I wanted to write that in inequality notation, 0 would be less than x, which would be less than 3. The range, though, those are all the y values you're hitting. So the maximum y value that we're getting closer and closer to is 2. And we're hitting all the y values on this graph that are below 2. So our range is y is less than 2. Or to state that, we're coming from -infinity all the way up to, but not touching 2. Looking at this for intercepts, there is no y-intercept It's never crossing the x-axis. I'm sorry, it is crossing the x-axis. It's not crossing the y-axis. So no y-intercept. But our x-intercept, so it's crossing at this point here when x is 1, y is 0. So 1, 0. And this one is not symmetrical with the x, y axis or the origin. So you guys should be able to look at graphs and answer, is that graph a graph of a function? You should be able to look at the graph, find the domain and the range, the intercepts, and notice if it's symmetrical across the x-axis, the y-axis, or the origin. But you should also be able, given the graph, to answer more questions. So for instance, let's say you have the following graph. And so we're going to use the graph here to answer the following questions. Okay, so looking at the following graph, we want to find the domain and the range of f. So notice that there's endpoints on here. There's not arrows. If there were arrows, that's telling me that it's following along in that direction. But instead, there's these points here. And so the smallest y value, I'm not a y value, x value that I'm hitting is -4. And the largest x value that you hit is 6. You're hitting all of the x values in between -4 and 6. So the domain in this case is the interval from -4 to +6, including, so we have a bracket. Or another way to state that is -4 is less than or equal to x is less than or equal to 6. The range, though, are all the y values that you're hitting on the graph. And so all the y values that we're hitting on the graph, so the minimum y value that this graph hits is y equals -2. The maximum y value that this graph hits is 3. And then it hits all the y values that are in between this -2 and 3. And so our range, we're starting always smallest to largest, -2 including, so a bracket -2 to 3 including, so a bracket. Or another way to express this is -2 is less than or equal to y is less than or equal to 3. So finding the intercepts, these are where we're either crossing or touching the x and the y axis. You erase all this stuff on here. So looking at this, let's look at our x-intercepts. So we're crossing at 0, 0. We're crossing at 4, 0, and we're touching at 6, 0. And so my x-intercepts are going to be the 0, 0, 4, 0, and 6, 0. The y-intercept, we only have one. It's crossing the y-axis at the point 0, 0. So the next question wants to know, how often does the line y equals -1 intersect the graph? Remember, if we have y equals some number, it's a horizontal line through that number. And so we're looking here, just get the ruler, at when y is -1. So if I did a horizontal line here through -1, and I want to look at how many times does this horizontal line intersect our graph. Well, if I look at this horizontal line at y equals -1, it intersects our graph here, and it intersects our graph here. So there are two spots where our line y equals -1 intersects the graph. So how often does a line x equals 1 intersect our graph? And so remember, x equals a number that was a graph of a vertical line through that x value. And so here we're looking at when is, just use our ruler to make a vertical line through x equals 1. And so if I'm looking at the graph of x equals 1, that vertical line, which was not quite vertical, but you get what I'm doing right here. It's only intersecting the graph once. So the line x equals 1 intersects our graph once. The next question wants to know, for what values x does f of x equals 3? Recall f of x is our y value. So f of x is another way to write y. Technically, our points x, y, another way to write this are x, f of x. So we want to know, when is y equal to 3? So let's look at doing a horizontal line through y equals 3. So y is equal to 3. Looks like if I did a horizontal line at y equals 3, notice that this just touches one spot. And so there's only one value of x that gives me back a y value of 3. So what value of x gives me y equals 3? Well, that is x equals 5. Gives me back a y value of 3. Almost similarly, the next question wants to know, for what values of x does f of x equal -2? So we want to know what x value give us y value of a -2. Well, if we look at the horizontal line through y equals -2, notice that this is only crossing or touching the graph once. And so there's only one x value that gives us a y value of -2, and that's when our x value is 2. Yes, I copied the graph again, so we have it, and we can continue to answer questions about the graph. So looking at the graph, you should be able to tell what is f of 0 and what is f of 6. Well, f of 0, you're looking at when my x value is 0, what is y when x is 0? Well, when x is 0, my y value, notice, is also 0. So f of 0 is 0. So we have a point at 0, 0. F of 6 So technically f of 6, we're looking at when x is 6, what is f of 6? So when x is 6, what is our y value? Well, when x is 6, our y value we get back is 0. So f of 6 is also equal to 0. Next, we're looking at this and we want to know, is f of 3 positive or negative? So we're looking at when x equals 3, is y a positive or negative number? Okay, well, let's look at when x is 3. When x is 3, going down on my graph and seeing where my point is, I notice that my point is below the x-axis. And so I notice that my point is negative. Another way to write that is f of 3 is smaller than 0 there. It's negative. It wants to know, is f of negative 1 positive or negative? So going to when x is negative 1, we want to know, are we falling above or below that x-axis? Well, when x is negative 1, f of negative 1 is above the x-axis, so it's bigger than 0. So we have a positive number. So what values of x gives us back f of x equals 0? Another way to state this is what value of x give us back y equals 0. Well, when y is 0, it happens to be when x is also 0. And the last piece, it wants to know, when is our function f of x less than 0? So another way to state that is, when is the graph falling below the x-axis? When are our y values less than 0? And so there's only one piece where we're going below the x-axis. And so we're looking at the x values that give us y values below the x-axis. We're not going to include 0 because we don't have the equal to part on that inequality. So we're looking at x values from 0, but not including, to x value of 4, but not including. So we can put it in interval notation, parentheses 0, 4, parentheses, or just so that you don't get confused, that's not a point. It's an interval starting at x equals 0, but not including, to 4, x equals 4, but not including. So we have 0 is less than, x is less than 4. So we're looking at f of x. We're given that f of x is equal to x squared plus 2 all over the quantity x plus 4. It wants to know, is 1/3 a point on the graph of f? Well, if 1/3 is a point on our graph, when we plug in our values here, this is saying x is equal to 1. When x is 1 is y 3/5. But another way to say y is f of x. So let's go in here and substitute. So if f of x is 3/5, is this equal to, and if it is, then it's a point on the graph, to the value of, now let's go in and let's plug in 1 wherever we see an x in f of x. So is it equal to parentheses squared plus 2 all over parentheses plus 4? Let's drop in our 1 for x. So let's simplify the right-hand side and see if we get back 3/5. If we do, we're good. If we don't, then it's not a point. So simplifying order of operations, we got 1 squared is 1, 1 plus 2, and our numerator is 3, all over 1 plus 4, which is 5. So plugging in the y value of 3/5 and the x value of 1, we do get a true statement. So yes, 1/3 is a point on our graph. Part B says, if x equals 0, what is f of x? What is the point on the graph? Okay, well, f of 0, this time we're going into our function, and wherever we see an x, we're replacing it with 0. So we have parentheses squared plus 2 all over parentheses plus 4. Go in and drop in 0 inside the parentheses and simplify. So we get 0 squared is 0 plus 2 is 2 all over 0 plus 4, which is 4. This reduces, they both 2 and 4 have 2 in common, so this reduces to 1/2. So if x is 0, f of 0 is 1/2. And the point on the graph is going to be x is 0, y is 1/2. So part C wants to know, if f of x is equal to 1/2, what is x? What are the points on the graph? So we're going to plug in 1/2 for f of x. Set this equal to our equation, x squared plus 2 times x plus 4. And we're going to solve for x here. So we can clear our fraction by multiplying through by our LCD, which is 2 times x plus 4 on both sides of our equation, so we can clear our fractions. Do something to one side, you got to do it to the other side of the equation. And so notice 2 cancels on the left-hand side, and we're left with just x plus 4 is equal to, the x plus 4's cancel on the other side. So we're left with 2 times this quantity, x squared plus 2. So I'm going to distribute my 2. I have 2x squared plus 4. So I want to solve for x here. So I have to look at what type of equation I have and how I'm going to go about solving it. I notice right here that I have a quadratic equation. So a lot of times with quadratic equations, we want to set it equal to 0. So I'm going to subtract x on both sides and subtract 4 on both sides. I get 0 is equal to 2x squared minus x. Well, 4 minus 4 is 0. I notice I can factor. So factoring is one way to solve quadratics. I can pull an x out of both of 2x squared minus x. That leaves me with 2x minus 1. Now setting each factor equal to 0 and solving for x. So I have x equals 0 and I have 2x minus 1 equals 0. So adding 1 to both sides, I get 2x is 1. Dividing by 2, I get x is 1/2. So we have 2 different points. When x is 0, y is 1/2. And when x is 1/2, we also get y is 1/2. The domain exclude any trouble spots. So we're excluding when our denominator is 0. So x cannot be -4. So it's all numbers except for -4. List the x-intercepts. Recall x-intercepts. Those occur when y equals 0. Or another way to state that, f of x equals 0. So let's go back up here to our equation and let's set our equation equal to 0. So I have 0 is equal to x squared plus 2 all over x plus 4. I can clear my fraction, multiply both sides by my denominator, x plus 4. So I get 0 is equal to x plus 4 cancel, x squared plus 2. I notice in this case, I could use the square root method because I have a perfect square in there and there's no x's outside of that perfect square. So if I subtract 2 on both sides, I get -2 equals x squared. I notice that if I took the square root of both sides, though, I get x is equal to plus or minus I root 2. This is not real. So we do not have any y-intercept or x-intercepts. So no x-intercepts. And the last one was the y-intercepts, if there is one, of the graph of f. So y-intercepts, recall, is when our value of x is equal to 0. So if we go back in here and we look at f of 0, that's going to give us back the parentheses where the x is, and then drop in 0 inside the parentheses. So we get 0 squared plus 2 all over 0 plus 4, which we saw was 2 over 4, which is 1/2. So our y-intercept, when x is 0, our y value is 1/2. So last example, we're given 2 graphs. We're given f of x, and we're given the graph of g of x. So looking at this picture, the graph of f of x is the line. It's red in this picture. And the graph of g of x in this picture is blue, which is the parabola. We want to find out what is f plus g of 2. So what this is saying is we're going over here and we want to look at what is f of 2 plus what is g of 2. Well, if I look at f of 2, so when x is 2, looking at what is my y value on that graph. Well, when x is 2, my y value is 2 plus g of 2. So again, I'm looking at when x is 2, going to my graph, what is g of 2? Well, g of 2, my y value when x is 2 is 1. So 2 plus 1 is going to give us back 3. So when we're looking at f of 4 plus g of 4. So going to x equals 4. For f of 4, my y value is 1 plus g of 4. So when x is 4, my y value here is -3. So we have 1 minus 3, which is -2. So the next one, we're given f minus g of 6. So we're looking at f of 6 minus g of 6. Locating x equals 6 on the graph. F of 6 is 0 minus g of 6. G of 6, my y value is 1. So 0 minus 1 gives me back -1. So the next one is g of 6 minus f of 6. We have 6 minus f of 6. Well, we already found those values from the one above. G of 6 was 1. G of 6 is 1 minus f of 6, and f of 6 was 0. So 1 minus 0 is 1. The next one is we're looking at what is f of 2 times g of 2. So when x is 2, y for f of 2 is also 2. And g of 2, when x is 2, y is 1. So we have 2 times 1, which is 2. Last case scenario example, we're looking at what is f of 4 divided by g of 4. So when x is 4, my f of 4 is 1 divided by my g of 4. When x is 4, g of 4 is -3. So looking at the graph, we can figure out what those operations of those two functions at a particular number is.